One of the most important applications of the theory of matrices is the theory of linear systems. Now, what is a linear system? It's a list of equations that looks something like this. So what we're studying here is a list of m linear equations with n variables. So every line here is some equation, and the way to interpret these equations is to think of these x's as unknown variables, and then think of everything else as some fixed scalars. So all of these a's and all of these b's are fixed scalars. When we're studying systems of equations or systems of linear equations, what we're generally interested in is solutions to the system. Now, by definition, a solution is any vector, bold x here, whose coordinates solve all of the equations. Let's take a look at some ideas here. So there's a certain vocabulary we use when we talk about linear systems of equations. One important vocabulary word is this term consistent. We say that a system of equations is consistent if it has at least one solution. So here's an example illustrating the idea of consistency. Here I have a system of 1, 2, 3, 4 equations with 1, 2, 3 variables. Now, I went home and I played with these equations, and I found that if you set little x1 equal to 5, little x2 equal to 2, and little x3 equal to 0, that gives us a solution to the system. All 4 equations are satisfied. I also found that if you set little x1 equal to 6, little x2 equal to 3, and little x3 equal to -1, also all 4 equations are satisfied. So here I'm illustrating that this system has at least 2 solutions because we've written 2 down here, which means this system is consistent. Now, the opposite of consistent is inconsistent. A system is called inconsistent if it has no solutions. Here's an example of an inconsistent system. Now, it generally takes a little bit of effort to determine whether or not something is inconsistent. So this is an example where we have 4 equations with 3 variables. And I know this is inconsistent. And why do I know this is inconsistent? Well, it turns out that if you add all of these equations together, you'll notice that all of the coefficients attached to x1 end up canceling out. -5x1 minus 4x1 plus 2x1 plus 7x1 equals 0. And then the same goes for the coefficients for x2 and x3. So if I add everything together, on the left-hand side of the equal sign, I'll get 0. But what happens on the right-hand side of the equal sign? We get 3 minus 1 plus 2 minus 3. Well, that's equal to 1. So adding all these equations together produces this new equation, 0 equals 1. Of course, 0 equals 1 is impossible, which means we'll never find a solution to this system, because if we did, we could plug that solution in, add everything together, and all of a sudden 0 would equal 1. Great. Now, how are matrices used to study linear systems of equations? Well, there's 2 ways that we'll do this. One way to do this is via the augmented matrix of a system. Let's illustrate the point of the augmented matrix with an example here. So here I have an example where I have a linear system of equations with 4 equations and 3 variables. Now, when I look at the data in this system, the idea here is that it's not really the variables that are playing the most important role here. It's the coefficients of the variables that define the system. So what we do is we go to every equation and we take out the coefficients of the variables and we put them into a matrix. So you'll notice here that the coefficients in the system for x1 are 3, 6, 2, and -7. That becomes the first column of my so-called augmented matrix. The second column will organize the coefficients of x2. That would be 7 and then 0 because there is no x2 in the second equation, 9 and 4. So that's my second column here. And then the third column of this augmented matrix gives me the coefficients of the third variable. In this case, that would be 4, 9, 0, and then, -4, 9, 0, and -12. So the first part of the augmented matrix representing a system is organizing all of the coefficients of all of the variables in the system. I like to call this the coefficient matrix. But it's not just the coefficient matrix that defines the system, because in addition to having these coefficients on the variables, we also have these constants to the right of the equals sign. So what we do is we take out all of those constants and we put them in the augmented matrix after the coefficient matrix, and for aesthetic reasons we separate these two things with a vertical line. So here we're inputting 11, -3, 2, 7 to the right of the coefficient matrix, separated out with a vertical line. I like to call this the augmented column. Now sometimes, especially when the context isn't totally clear, I will label the columns of the coefficient matrix with the variables where those coefficients came from. So sometimes that's useful for communication purposes. Great. Now, there's an alternative way to represent the data in a linear system of equations with matrices, and this is through the concept of matrix vector multiplication. So the idea is that I can distill the information in a big linear system of equations into a single matrix equation of the form AX equals B, where X is a variable vector. Again, I think an example is the best way to illustrate this point. So here, the example we're looking at has 4 equations with 2 variables. And so the coefficient matrix of this system is a 4x2 matrix. It has 2 columns, and each column is organizing all of the coefficients of the variables in the system. Now the idea is that I can define this vector B as the vector that we previously called the augmented column in the augmented matrix. So in this case, that's the vector with coordinates 11, 2, 8, and 14. And then now I'm going to store the information of the variables, so the data of x1 and x2, in this variable vector called bold X here. So the idea is that the data of this linear system of equations is the same thing as this matrix equation, AX equals B, where X is an unknown vector here. So now we can sort of distill the problem of finding solutions to our system to the problem of solving AX equals B for X. Excellent. Now, solving systems of equations is a really important part of mathematics, but the truth is that it's somewhat difficult to do in general, although we will solve this problem. However, if our matrix is in reduced row echelon form, this problem is straightforward and there's a sort of procedure to it. So let's say that I'm studying an augmented matrix that's in reduced row echelon form. So that's exactly the example we're looking at here. Now, this augmented matrix is representing a system that has 1, 2, 3, 4 equations and 5 variables. So the first thing I do when I'm working with a reduced row echelon form matrix is I locate my pivot positions. And now the idea is that when I'm in reduced row echelon form, there's a naming of the variables. So variables that occur in pivot columns are always called dependent. So in this case, my pivots are in columns 1, 2, and 5. So I call variables x1, x2, and x5 the dependent variables of this system. The other 2 variables in this system are in non-pivot columns. We refer to those variables as free variables. So in this system, the free variables are x3 and x4. So when I'm in reduced row echelon form, it's always easy to locate the dependent and free variables by figuring out where the pivot and non-pivot columns are in the coefficient matrix. Okay, the next piece of vocabulary when we're studying a reduced row echelon form system is consistency and inconsistency. So in general, it's not always quite so easy to tell whether or not a system is consistent or inconsistent by just looking at it. But if we're in reduced row echelon form, this actually is very easy. Inconsistency occurs if there is a pivot in the augmented column of our reduced row echelon form augmented matrix. Here's an example illustrating the point. This is a perfectly good augmented matrix representing a system with 4 equations and 4 variables. I have 2 pivots in the coefficient matrix in the first and second columns. So under our previous naming convention, we would say that x1 and x2 are dependent and x3 and x4 are free variables. However, I'm not done analyzing this reduced row echelon form matrix because I actually have another pivot here in the last column. That's a pivot in the augmented column. And this means that our system is inconsistent. And why might that be? Well, if I look at the third equation in the system, all of the coefficients for the variables are 0. So on the left-hand side of the equal sign, I get 0. But then on the right-hand side here, I have a 1. That tells me that the third equation is 0 equals 1. And of course, that's an impossible equation. So if there's an impossible equation in the system, of course, the system cannot be solved. Now, the opposite of course, of inconsistent is consistent. A system in reduced row echelon form is consistent if the augmented column contains no pivot. Great. Now, when we're studying a system that's in reduced row echelon form represented as an augmented matrix, the rank, remember, is the number of pivot columns. And if we think about what that means, well, remember, the dependent variables are the ones that occur that correspond to pivot columns. So the rank of the coefficient matrix is always the number of dependent variables. In our example here, we're studying an augmented matrix in reduced row echelon form, representing a system of equations with 3 equations and 5 variables. My pivots in the coefficient matrix are in the x1, x2, and x5 positions. So x1, x2, and x5 are my dependent variables, and the rank of this system is also equal to 3. So the dependent variables are x1, x2, and x5, and the rank of the coefficient matrix here is 3. On the other hand, the nullity of the coefficient matrix, remember that's the number of non-pivot columns, and the variables corresponding to non-pivot columns are called free. So the nullity is the same thing as the number of free variables. In this case, my free variables are x3 and x4, and the nullity of the coefficient matrix equals 2. So when I'm in reduced row echelon form, I can easily identify the dependent and free variables. The number of dependent variables is the rank of the coefficient matrix. The nullity of the coefficient matrix is the number of free variables. And I'm also able to quickly identify whether or not my system is consistent by checking whether or not there is a pivot in the augmented column. This leads us to what's called the Rouche-Capelli theorem. The Rouche-Capelli theorem tells us that every reduced row echelon form system falls into one of 3 broad categories. The first category is the category of inconsistency. This is the situation where your system just has no solutions. And again, you can easily identify whether or not your system is inconsistent when you're in reduced row echelon form by checking whether or not there's a pivot in the augmented column. Our second broad category here is the category of consistency with exactly one solution. As we'll see in examples in a moment, this is exactly the situation where your system is consistent. So in reduced row echelon form, that means there's no pivot in the augmented column. But also where you have no free variables. So that would be consistency with exactly one solution. And then the third category, and perhaps the most interesting, is the category of consistency with infinitely many solutions. This occurs when you're consistent, again meaning there's no pivot in the augmented column, but free variables exist in the system. So ultimately what it comes down to is there are no solutions if you're inconsistent. And if you're consistent, there will either be one and only one solution or infinitely many solutions. And whether or not you have one and only one or infinitely many is controlled by the existence of free variables, which is ultimately the same thing as the nullity. So if the nullity of our coefficient matrix is 0, that means there are no free variables. And if we're consistent, that means there's exactly one solution. On the other hand, if you're a consistent system, but the nullity of the coefficient matrix is greater than 0, that means you have at least one free variable, which means you'll have infinitely many solutions. Okay, so that's a broad taxonomy of all systems in reduced row echelon form. Every system in reduced row echelon form fits into one of these three situations. So, of course, that's all well and good, but what we really want to do is we want to generate solutions to systems. Well, there's a procedure for doing this when we're in reduced row echelon form. So the setup here is, let's say that we're studying a system, Rx equals B, where the system is in reduced row echelon form, and let's say that we know we're consistent. Again, this is easy to determine by checking whether or not there's a pivot in the augmented column. So the procedure for solving the system is as follows. The first thing we do is I like to relabel all of the free variables as with new labels, and I typically use C1, C2 down to CK, where K here represents the number of free variables. Then the structure of reduced row echelon form always allows us to go equation by equation and solve for exactly one dependent variable in terms of our free variables. Then, after we've solved for every dependent variable in terms of the free variables, this ultimately allows us to express our general solution to the system, vector x, as x sub p, that's called a particular solution, plus some linear combination of vectors where the weights here are equal to the scalar symbols we used in step 1 for the free variables. Okay, so I think the best way to illustrate that step-by-step process is through examples. So let's look at an example of a reduced row echelon form system. So here I have a reduced row echelon form system, and this system represents a system with 2 equations and 4 variables. Note that this is in reduced row echelon form. I have my 2 pivots here in columns 1 and 3. Now, once I've identified that my system is in reduced row echelon form, I can do my initial analysis. First of all, there's no pivot in the augmented column here, so I know that this system is consistent. Second of all, there are 4 variables, but the rank of the coefficient matrix is 2, which means there are free variables. The dependent variables here are the ones corresponding to pivot columns. That would be x1 and x3. And the free variables here are the variables corresponding to non-pivot columns. Those are columns 2 and 4. So I now know which category of the Rouche-Capelli theorem I'm in. I'm consistent, which means I'll either have one or infinitely many solutions. And because I have free variables, I actually know that I'll have infinitely many solutions. So let's now proceed to follow our step-by-step process in order to write down all solutions. So if I look at the 2 equations articulated by this augmented matrix, what are they? The first one should be 1 times x1, so x1, plus 3 times x2, plus 0 times x3, plus 6x4 equals 7. So that's my first equation here. The second equation comes from the second row of the augmented matrix. It should be x3 minus 5x4 equals 1. Now, remember, the first step of this procedure is to relabel the free variables. And the free variables here are x2 and x4. So x2 is my first free variable, so I'm going to relabel it as c sub 1. So I'm going to go here. This is the only occurrence of x sub 2 is in the first equation. I'm going to replace it with c sub 1 here. The next free variable is x sub 4, so that's the second free variable. I'm going to relabel x sub 4 as c sub 2. X sub 4 occurs in both equations, so I have to change it in both equations. So now, if you look at, after you've done this, you look at every equation, you'll have x's, but there will only be one x per equation, and that x will be a dependent variable. This allows us to go now equation by equation and solve for the unknown x. The first equation is really 7, or x1 equals 7 minus 3c1 minus 6c2. And the second equation is x3 equals 1 plus 5 times c2. So now I've successfully solved for my dependent variables in terms of my free variables. Excellent. Now what I can do is I can write down the general solution vector. Remember, this system had 4 variables, so any solution to this system looks like x1, x2, x3, x4. But the thing is, I'm not allowed to just input whatever I want for all 4 variables. what do I do? Well, I address this issue by accounting for what we just solved for. We said x1 was 7 minus 3c1 minus 6c2. So I set x1 equal to that quantity. Then we said x2 here was equal to this relabeling c sub 1. So that goes in my second coordinate for my solution vector. The third coordinate x3, we solved for this previously. That was 1 plus 5c2. So that goes in my third coordinate of my solution vector. And finally, we've said previously that x4, that was our second free variable, which we set equal to c sub 2. So this goes into my fourth coordinate of my solution vector. Now we get a better idea how the solutions to this system behave. I'm allowed to plug in any numbers I want for c1 and c2. That will set the values of the second and fourth coordinates of my solution vector. But once those values are set, my values of the first and third coordinates are determined for me with these formulas. Now, I always like to go a step further and separate this out. So what I do is I go inside of this solution vector, and I keep track of the different types of coefficients. You'll find that some coefficients inside of this solution vector are not attached to any c's. In this situation, some are attached to c1, and others are attached to c2. So what I start by doing is I start by going entry by entry and asking myself which terms do not have a c attached to them. And in this case, in the first coordinate, I have a 7. In the second coordinate, there's no terms without a c, so that will be a 0. In the third coordinate, I have this 1, and then in the fourth coordinate, there's no term without a c, so that that coordinate will equal 0. So my x sub p here is 7, 0, 1, 0. Then, in this other vector x sub 1, I'm going to collect the coefficients of c sub 1 in the solution vector. In the first coordinate, the coefficient is -3. In the second coordinate, the coefficient is 1. And then the last two coordinates don't have a c sub 1, so the coefficients are equal to 0. Finally, in this last vector here, x sub 2, I collect the coefficients of c sub 2. So I go to my solution vector, and I go coordinate by coordinate to figure out the coefficients of c sub 2. Here I should get -6, 0, 5, 1. So this gives me a nice view of all solutions to my system. Every solution to this system can be written as this particular solution, 7, 0, 1, 0, and then we get infinitely many more by adding any linear combination we want of this vector x1 and this vector x2. So this system has infinitely many solutions, as promised by the Rouche-Capelli theorem. Here's another example. This is a reduced row echelon form system. Is it consistent? Well, yes, because I have 3 pivots, but they're all in the coefficient matrix. So according to Rouche-Capelli, I'll have one solution or infinitely many, depending upon the number of free variables. But I notice here that every variable corresponds to a pivot column. That means every variable is a dependent variable, and there are no free variables. So Rouche-Capelli promises that there's only one solution to this system. And sure enough, if I just look at the 3 equations, the 3 equations are telling me what x, y, and z have to equal. The first equation is telling me x has to equal -3. The second equation is telling me y has to equal 2. And the third equation is telling me z has to equal 9. So there's only one solution to this particular system. It's the vector -3, 2, 9. So this is an example of a consistent system with exactly one solution. Excellent. I'd like to conclude this lecture by discussing what to do if our augmented matrix is reduced but not in reduced row echelon form. In other words, if it's in row echelon form. Well, here's an example of an augmented matrix in row echelon form. Remember, my pivots don't have to equal 1. And also, I'm allowed to have non-zero entries above pivots. That's what distinguishes between reduced row echelon form and row echelon form. Well, if I'm in row echelon form, this language of dependent variables and free variables still totally makes sense, and the idea of consistency directly carries over. So in this situation, I have 3 pivots in the coefficient matrix in columns 1, 2, and 5. So the dependent variables of this system are x1, x2, and x5. I also have 2 non-pivot columns in the coefficient matrix. Those are columns 3 and 4. So the free variables in this system are x3 and x4. Finally, there's no pivot here in the augmented column, so I know that this is a consistent system. So no pivot in the augmented column, consistent. And so the Rouche-Capelli theorem also extends to augmented matrices that are in row echelon form, even if they're not in reduced row echelon form. Every single row echelon form augmented matrix represents a system that falls into one of these 3 categories. One possibility is inconsistency. This means your system has no solutions, and numerically you can detect this if you're in row echelon form by whether or not you have a pivot in the augmented column. Another possibility is that your system is consistent with only one solution. That occurs if there's not a pivot in the augmented column, which ensures consistency, but also if there's no free variables. And finally, there's the category of consistency with infinitely many solutions. This occurs if you're consistent, meaning there's no pivot in the augmented column, and also if there's at least one free variable, like this third archetype. Again, the number of solutions to a consistent system is ultimately controlled by the nullity of the coefficient matrix. If the nullity of the coefficient matrix is 0, that means there's no free variables, which means there's only one solution to the system. And if the nullity is greater than 0, that means there's at least one free variable, which will give us infinitely many solutions as long as we're consistent. So let's look at an example of actually solving a system represented as a row echelon form augmented matrix. So here I have an augmented matrix representing a system with 2 equations and 3 variables. You'll notice that my pivots here are -2 in the 1, 1 position and 3 in the 2, 2 position. Now there's no pivot in the augmented column, which means this is a consistent system. Also, the rank of the coefficient matrix is 2, but the nullity equals 1. So there's at least one free variable. In this situation, the dependent variables are x1 and x2, because those are the ones that correspond to pivot columns. And there's one free variable, that's the variable x3, which does not correspond to a pivot column. So what am I supposed to do if I'm in this situation? Well, since I've identified the free and dependent variables, I can once again relabel the free variables with these new labelings, C1, C2 to CK. There's only one free variable here, that's x sub 3, which I'm going to relabel as C sub 1. So I go to every equation here, and I relabel x sub 3 as C sub 1. Now, remember, this is not a reduced row echelon form system. This is a row echelon form system. Unfortunately, because I'm not in reduced row echelon form, I can't just easily go from equation to equation here and cleanly solve for a dependent variable, because in my first equation, there's actually 2 dependent variables. However, the important insight to make here is that if I start at the bottom, there will always be only one dependent variable in that equation. And in this case, that's x sub 2. So what I'm going to do here is I'm going to go to the second equation, and I'm going to solve for x sub 2. It turns out when I solve for x sub 2 here, what should that be? That should be 6 plus 15c1 all divided by 3, which simplifies to 2 plus 5c1. So I've successfully solved for x2 using the last equation. Now the idea is that I have x2 represented in terms of my free variable. I can take that expression and put it into the equation above it. So I can now replace x2 with 2 plus 5c1 in the first equation, and then cleanly solve for x1. When I did this, I got this quotient here. So now, x1 has successfully been written in terms of c1, and x2 has successfully been written in terms of c1. This allows us to write down the full solution vector. Remember, there are 3 variables here, so any solution to the system has 3 coordinates, x1, x2, x3. Well, I'm not allowed to just plug in any x1, any x2, or any x3, but I am allowed to say that, well, x3 was equal to C1. So I can label x3 however I want. Once that value is set, I then proceed to input my value for x2, which we said was equal to 2 plus 5c1. And then I can go to x1 and insert what I solved for previously. If I clean up my solution here, x1 ends up simplifying to negative 13 minus 13c1. So the idea here is that in this solution vector, yes, there are 3 coordinates, but I only have 1 degree of freedom to choose those 3 coordinates, and that's the choice of c1 here, which is equal to the 3rd variable. Now, once again, I like to separate this solution vector out as x sub p plus, in this case, just c1 times a vector x1. xp is organizing all of the coefficients in my solution vector not attached to c1. In this case, that should be negative 13 to 0. And then this vector x sub 1 here is organizing all of the coefficients of c1. Well, those coefficients should be negative 13, 5, 1. So that's my vector x sub 1 here. So this process, when you're in row echelon form, will always play out like this. We start at the bottom and solve for dependent in terms of the free. Then we plug in that formula into the next equation above, solve for the next dependent in terms of the free, so on and so forth. This will always work, and this is what's called back substitution. So back substitution is our technique for solving row echelon form systems that aren't in reduced row echelon form. So that concludes the lesson. Let's take a look at the Sage module on the course webpage. There's only 2 calculators here. The first calculator just shows you the syntax for constructing an augmented matrix. So I've predefined a matrix A here, and I've predefined a vector B. The idea is that if you want to tack on B to the as the last new column of A, the syntax for doing this is A dot augment open parentheses B, comma subdivide equals true. Subdivide will give us the aesthetic line before the augmented column. So if I click evaluate here, this will produce my augmented matrix that I'm working with. So if you change around the numbers in both A and B, you can print out whatever augmented matrix you're interested in. And following that idea, I've written some code in the second calculator so that if you write down a system in augmented form where A is the coefficient matrix and B is the augmented column, the code down here will do what? If I click evaluate, it will analyze the system. So what it'll do is it'll tell me whether or not the augmented matrix is in row echelon form. And if it is, it'll tell me whether or not the system is consistent. It will identify the dependent and free variables, and then it will tell me the number of